Hi, welcome back to Data Management with Stata. I'm Ben Littenberg. Here's module number 4. Necessity is the mother of invention. It's all about creating variables. And this is the agenda for module 4. Please read chapters 5 and 7 of your textbook. You can skip sections 5.8 and 5.9 because we'll do them later. And we'll talk in this video about why we care about creating variables, how to create them, and we'll go over some commands and some functions that are useful in creating variables. We'll spend some time talking about how to convert string variables to numeric variables and vice versa. And we'll also talk about how to label them. I advise you open up Module 4 dataset.dta in Stata and follow along at home. And I've done that here as well. So here's Module 4. And we'll start off by doing a description, D, and what we see is that there's 1,008 cases, 26 variables, and it's got some floating variables and some strings and the usual mix of things. And we're going to be working with this for our examples. Okay, why make new variables? Well, one main reason is to make our analysis more tractable. For instance, we might have string numerals that we want to do numeric analysis on, so we have to convert them to numbers. Sometimes we need to go the other way. We might have string categorical values that we need to turn into labeled categories. We might want to dichotomize or categorize non-normal variables for things like logistic models. We might want to combine various categories. We might want to just generally transform data that don't meet assumptions, sometimes called badly behaved data. For instance, highly skewed data, sometimes if you take a logarithm or a square root, you wind up with data that are normal and you can use classical statistics on it. Another reason to make a new variable is to make our analyses more understandable. For instance, proportions are sometimes easier to explain than means or distributions in general. The units may be opaque. Perhaps we have something measured in furlongs per millisecond and you want to convert it to miles per hour. Very small units can give apparently small effects. For instance, the odds ratio or the relative risk per milligram might be a very, very small number, which is a little hard to wrap your head around. But when you express it as the relative risk per gram, it has a lot more accessibility to your audience. And of course, graphs may require transform variables to make them look good on the screen. Here's our first two commands that we want to talk about, generate and replace. Generate makes a new variable. For instance, we already have a variable called duration, which is labeled as the duration of diabetes, and it's in years. Let's calculate how many months each subject has had diabetes. So here's our diabetes duration, summarized duration, and we discover it runs from 0.02 of a year, which is about 1 week, up to 62 years. And we can generate a new variable called months, and it will be equal to the units in years, which is called duration, times 12 months per year. And what we discover now is when we summarize months, we still have 957, there's still 51 missings, but the mean is, instead of 10 years, it's 120 months, which is about right. The 2% of a year turned out to be just about a quarter of a month, 1 week, and the 62 years is now 744. And so it did exactly what we thought it would do, and the new variable is now over here. It made it to the list. When you create a new variable, Stata puts it to the bottom of the list. We have two variables already that carry the weight of the subject in kilograms, and another one that's the weight of the subject in meters. And we want to calculate body mass index, which we'll call BMI. But let's only do it for the first 300 subjects. Let's assume the next subjects from 301 through whatever it was, 1008, are not eligible for BMI for whatever reason. So what we can do here is generate BMI is equal to the kilograms. Let's remember the formula. It's per meter squared divided by meters to the second power. That's how you do a square. And let's do that only in 1 through 300. And therefore we have 710 missing values. Now when we summarize BMI, we only have 298 cases. The reason being that 2 of the 300 didn't get calculated, probably because they were missing either kilograms or meters. And what we discover is 32 is the average, 32.5, which is obese and typical of adults with diabetes. And we have, it ranges from quite underweight to massively obese. The next command we want to talk about is replace. Now, replace does not create a new variable, but it changes the value of a current value of a variable with a new value. So let's take a look at the z variable. Again, I'll summarize it. And what we see is that z has a mean of half, a standard deviation of 30%, and it ranges from, well, from just about 0 to just about 1. In fact, if we code book z, we discover that it's got a 1008 unique values, no missings out of 1008. So every subject here has got a different value of z. But we want everyone to have the same value of z. So we're going to replace z with 123.8 for obscure analytic reasons. We'll type replace z is equal to 123.8. Now, if I codebook z, now I zip back up to the codebook command by just hitting page up a couple of times. I could also have picked it off of the left-hand variables or command menu there. Codebook z, now we see that the range is 123.8 to 123.8, and there's only one value for all 1008. So it did what we thought it should do. We've got another problem variable, and this one is called sysbp. So if we codebook sysbp, we discover that there's no missings, but there's a bunch of 999s. In fact, if we summarize sysbp in detail, we get what we see is that well, the 4 largest, at least, are 999s. And then it turns out, we remember, oh, our data entry system assigns 999 when the data are missing or unknown. So we need to fix that in Stata, because the average looks like it's 147, which is really bad. But that's not typical of the average. In fact, or not typical of the distribution. Let's do a histogram and see that, oh yeah, most of our subjects are down where we expect blood pressures to be, in about, a little less than 100, maybe a little more than 200 on a bad day. And then we have a bump here at the 999 value. So we want to get rid of that. And what we're going to do is replace sys blood pressure equal dot, the missing value, if sys blood pressure is exactly equal to 999. Now, unlike generate, which I could use gen as a shorthand, replace, you're not allowed to use a shorthand because it's could make a mess with that command, so you have to be a little extra careful. So we're going to do replace sys blood pressure is equal to dot if sys blood pressure is exactly equal to 999. And there we go. 9 changes have been made. I'm going to go up to the histogram again, and when I do it this time, we get a nice distribution of blood pressures right where we expect them to be. And when I go back up and do the code book, or let's do the detailed summary, now we discover that the mean has dropped from 147 to 140, which is a much better mean systolic, but the median, of course, did not drop hardly at all. Well, it looks like it didn't drop at all, which is typical of a large sample size with a few outliers. Okay, now be careful here. Those old values of 999 are gone, just like the old distribution of Z is gone. So if you're not sure that you want to do that replacement, you might want to create a new, perhaps a temporary variable before you replace all the old ones. Okay, let's see. So generate and replace are our favorite commands in this setting, but let's talk about some functions. Okay, well, functions can do all sorts of transformations of your data based on math, logic, all sorts of other strategies. And we'll do a couple of these. For instance, you can create a new variable that is the absolute value of some previous numeric value. So this is the absolute value function, which is, as you remember, it's the value of the original, unless the original was a negative number, in which case it's the positive equivalent of it. So let's create a new value y, which is the absolute value of x. And we'll do that by typing generate y is equal to the absolute value of x. So here, the command is generate y. Generate is the verb, y is the subject, and the object is the absolute value of x. So we can use a function on the right-hand side of an equation, and it will pour into the variable on the left-hand side. So when we do this, what we're going to do now is let's summarize x and y. So the maximum of x was 3.5 and the maximum of y is 3.5. But the minimum of y was minus 3. So this was flipped over to positive 3. What I'm going to do now is list x and y in, let's say, the first 25 cases. And we discover that a minus 0.7 becomes a plus 0.7 and minus 17, but a plus 82 stays a plus 82 because that's what an absolute value does. Once again, the new variable is sitting in our variable list. Here's another function we can do. We can exponentiate a number. For instance, we can create a variable that is exponential of x, or if you like, e to the x. It's the anti-logarithm. The e is Euler's number, 2.7, etc. So if we want to generate, I believe we called it x exponent, let's take exp of y. Nope, of x, I'm sorry. And now I can list x and x bar exp. And what we see here is numbers near 0 get exponentiated close to 1, and numbers near 1, if we can find one here, will be just short of Euler's number 2.7. So kind of what we expect. We can also take the logarithm. So if we want to take the logarithm of, well, we should do it for y. So let's make it generate y log. Generate y natural logarithm is equal to the natural logarithm of y. And again, we can do the list, or we could just summarize y and y log. And the natural logarithm of 0.77 is minus 0.67, of 3.5 is 1.2, and so forth. Okay, here's a slightly different twist on a function. This is the maximum of a list of variables. So it says for each row, for each case, for each subject, go through all the variables in this list and find the biggest one. And so here it's the maximum of age, HDL, and we could have kept going, but I just said do it for 2. So we're going to generate a new variable called max age HDL. Generate max age HDL is equal to the maximum of age, comma, HDL, close the parentheses, and I'm sorry, I did a little typo, so it's going to be MX. Well, let's fix that, because those are the sorts of things that you better fix while you're doing it. So let's rename MX age HDL MAX age HDL. And what did I do wrong? So let's do so I managed to make an error fixing an error, and what we have is right over here. I shouldn't have put that space in. Now it's a lot happier, and the variable is max age HDL. So let's now list age HDL, and I'll just click over here to get it. Age HDL, max HDL, and let's just pick some from the middle of the list, say 500 through 530. And here we've got, well, people with an HDL. Oh, it looks like this was sorted on HDL. So here's someone who's older than their HDL, so the value went to their age, and that's true for most of these people. But here's someone who's younger than their HDL, so the value became their HDL value, and there's a couple of those. We can do the same thing with minimum, and this, it might be a handy function to have. For instance, we might not create a new variable, but just list the results of problem cases with a test. So perhaps we want to know the subject numbers and their blood pressures if the minimum of their systolic and diastolic is their systolic. In other words, their systolic is less than or equal to their diastolic. And I'll leave that for you to run at home. here's a function that rounds numerics. You can, for instance, replace age to the nearest tenth. So as you can see, our age variable is calculated out to a ridiculous level of specificity. Perhaps we would like to do replace age is equal to round age, and do it to a tenth of a year. Now, if we do the same command we did before, we discover that age has been rounded uh, and correctly. The 83.46 went up to the 83.5, for instance, where the 63.93 went down to the 63.9 instead of up. And that's the correct way to handle it. But what you'll notice is that the age changed, but not, of course, the variable we created from age earlier. So you got to keep in mind that the chain and sequence of events here will influence which ones get changed when. Now, rounding, we told it to do it to the nearest tenth. If we hadn't given it any value here at all, it would have rounded it to the nearest year. So let's try that. And now let's do replace age is equal to round of age with no option in there. And now when we list those same variables, we discover that where it used to be to the nearest tenth, it's now to the nearest unit. And we can round it to the nearest decade or the nearest century or the nearest millennium, in which case there won't be much information left in the variable. Here's a very handy function if you're trying to just generate random numbers, perhaps to sort data in random order or to select a subset of patients. Random uniform, R uniform, just generates a number randomly selected from a uniform density between 0 and 1. So let's create a variable called uni, and we'll just base it on the uniform distribution between 0 and 1. If we now do a histogram of uni, what we see is that it's roughly, there's not a lot in the way of peaks and valleys in these data. It's essentially a rectangular or uniform distribution. There's another, there's actually quite a number of these R functions, random functions. We could create one based on the normal distribution. And if we generate a norm as a R normal, and we now histogram norm, what you see is it really looks quite a bit like a normal distribution now. So those are handy for a variety of statistical and simulation techniques. Here's some more functions. These concentrate on strings. So if you've got a string variable that happens to contain numerals, for instance, instead of saying the current year of 2019, it's got a 2019 represented as the characters rather than the number. Well, you might want to convert that to a real number. Now, we've got a number represented that way in our database. It's something called PCS string. And PCS string has got values like 27.96808, and notice it's in quotes because it's a string value. Now we might want to generate perhaps a PCS numeric. And so what we can do is generate PCS numeric by using the function real PCS string. Now we can list both PCSs, and I'll just use the asterisk wildcard, and let's do that in the first 20 cases. And what we discover is that the string value 31.38 works out perfectly well now. The string function takes a numeric and makes it into a string. So if we happen to want the string equivalent, well, we could take one that we already had, which is MCS numeric, and we can generate MCS string is equal to the string equivalent of MCS numeric. And now let's list the MCS again in 1/20. And here it is as a numeric. It looks identical. Strings are pretty complicated, and you can get quite fancy. For instance, you can have a long string and be looking for a particular substring. For instance, in my name, you might want to know where is the first J? Well, in Benjamin, it's in position 4. So if you said string position Benjamin J, it would generate a 4. Well, actually, let's try that out. We'll just ask it to display the string position inside the string Benjamin, and we're giving it an explicit string, not a variable here, and we're looking for a lowercase j. Now, case is going to matter. And sure enough, it says it's in 4. If we ask it where a z is, it says there isn't any. If we ask it for is there a jam, it'll also say 4 because jam starts in the 4th position. If we ask it for NJAM, it'll now give us a 3 because NJIM starts in the 3rd position. Now, in this data set, there's a variable called record. And let's take a look at that. We'll codebook record and see what we got. Well, it turns out there's 1,008 unique values. They're all strings. And what we discover is that they have some numbers, a letter in the middle, and some numbers. And it turns out in this data set that subjects that were assigned to category A were in the early wave of the study. So we would like to generate a variable called early. Let's see. How did I propose doing this? I want to be consistent with you. It's is equal to string position inside record. Now, you don't need quotes here because record is the string variable name that will be a different string value for each subject in here. And we're looking for an uppercase A, which does have to be in quotes. And if we hit return now, we will discover that some people have it in the 1st position, the 2nd position, the 3rd, the 4th, the 5th, and quite a few people have it will have a 0. But that's not exactly what we want. We just want to know, do they have it at all? If they do, they're in the early group A. So what we're going to do is turn this into a logical statement or a Boolean statement. Now it says string position of the record. Where is, what is the string position of capital A in the record string? And is it greater than 0? If it's greater than 0, this is a true statement, and therefore early is set to true. If it is not greater than 0, for instance, in this case here, it will be equal to 0 because there is no capital A in that string. Then early will be set to 0 because string position will not be greater than 0. So that executed. Let's list, or let's type better. List record and early. And let's do it. Let's still use the first 20 records, which turned out to have nobody with an A. So there we go. We got a B here. It's in position 4, but there's no A, so it gets a 0. We got a B here in position 3, no A, it gets a 0. So forth. Here's a C in position 2, doesn't count. Oh, here's an A, it's in position 2, it gets a 1. Another A in position 2, A lot of A's in position 2. Don't see any A's in other positions, but if they're there, it would catch it. It looks like our code has worked. Let's tab early and see what we got. It looks like there's 300 in the early group and 708 in the not early group. Once again, this new variable is here. Now I'd like to point out that early is a numeric value that was derived from strings, and it's got the values of, they're all zeros and ones, so it's a dichotomous. Now, we've got another string called SID, subject ID, and perhaps we don't want to find a string as this one does. We want to pull out a substring. So we start with our string and we say from character start for this many characters. Pull that out and stick it in a new string. So let's take a look at SID. And let's do the first 30. And what I discover is that SID always has a number in the first position, followed by 3 characters of alphabetic, and then some more digits. And I want to know a separate variable that pulls out this set of 3 characters because they represent what subject group the subject is in. So what I am going to do is generate the subject code as the substring from position 2 forward 3. So we're going to generate sbar code is equal to the substring of the string variable SID from position 2 for a length of 3. And now I'm going to list SID and the S code, and let's see how we did. It worked. We pulled out an ABB and ABB. This one's a JBB and another JBB, and so forth. And now, if we tabulate S code, I discover that there's only 4 distinct codes: ABB, ABQ, JBB, and JRK. Now, it turns out that there was a typo in this. It wasn't supposed to be a Q, it was supposed to be a G. In other words, these ABQs are supposed to be ABGs, but G and a Q, somebody has dyslexia and it snuck into our data. So let's do a substitution. So whereas before we were looking for the substring, this time we want to substitute into a string. We're going to take a string, we're going to look for the old substring and replace it with the new substring, and we'll do it this many times. So replace scode is equal to substitute in string of scode itself, and we want to get rid of any Q's we have and replace it with G's. And we want to do that, well, there's probably only one in any given record, but we want to do it as many times as it takes. So we can give that a missing value, which is a do it until you're out of opportunities. And it made a 196 changes, which is reassuring because that's how many ABQs we have. And if we now tab scode, sure enough, it's got ABG and not ABQ. So that worked. Here's another string function that's really quite handy. And it says, take a variable, some sort of, it's a candidate, and check to see if any of these strings or values are in the candidate. So, for instance, maybe we don't want to generate a new value, but we could just count within group how many A's, how many have are an A, a C, or a D. Well, let's take a look at group first of all and make sure we know what we're dealing with. So group is a 1-character long string that is either A, B, C, or D. And now I might want to count if group is equal to A, and I should get 282. I could also say if it's equal to A or group is equal to B. Okay, so now that's 282 for the A's, 428 for the B's. You add them together, you get 710. But maybe we could use this command instead. Count if in list group and say, well, is it an A? Is it a B? And when we do that, we get the same 710. Well, that's, not a big advantage. But now C is the 966. Okay. And then maybe we want some different combination like A, B, and D. So this option allows you to try all different possibilities, and it can be very, very handy in processing complicated string variables, but also numeric variables can be used this way. Perhaps they're ID numbers or zip codes, for instance. And we could create a list of all zip codes that are, metropolitan areas and check, is this subject's zip code in this long list, and confirm, assign them to a metropolitan zip code or rural zip code on that basis. Here's my next command. It's one of my favorites. It's calledegen. It's just like generate. It creates a new variable. However, it does a lot of extra things that gen doesn't. It's basically all those things that we all wished generate would do, and they added it on. For instance, if you have a continuous variable, we'll call it var name, we can cut it. You can cut it into bins, for instance, at a particular number or into so many groups. So let's cut age. Now we know that age runs, well, let's take a look. What is our distribution of age? Age runs from, well, 22 to 93. We expect adults in this thing, so 19 would have been about the lowest, or 18 would have been about the lowest we'd expect. So I'm going to create an age category, and I'm going to, but I'm not going to use gen, I'm going to use egen, because I want to cut age, and I'm going to have an option here to tell it how to cut it, and you have to give it that, and I'm telling it to cut it at, oh, let's say, well, let me see, I had some clever ones here, 19, 30, 50, 65. So 19, 30, 50, 65, and was it 80? Yeah, 80, and then finally the outrageous out of range ones. So when I do this, oh, and let's tell it to label it, which is turns out to be a very nice way to do it. So now I can tab age cat, and what I get is there's a category that's 19 to less than 30. There's 3 people in it. From 30 through the 40s, and but less than 50, there's 113 in there. So you know, and these are perhaps young, you know, adult, middle-aged, seniors, and the very old. These are categories we might reasonably care about. And so we now have a variable that tracks that very nicely. Now, if we tabulate it again and say no label, what we discover is it's assigned them to groups 0, 1, 2, 3, 4. There's another way to do that, and that's with the group. So perhaps I want to get quintiles. Let's do age 5 is equal to cut age, and this time just do it group into 5 groups. And let's not put a label on this time and see what happens. And so now if we tab age 5, we discover that it just assigned them to these, and it put as close to 1/5 of subjects into each group as it possibly could. It can't split these exactly because of ties, but it got as close as it could. And if we now want to look at by sort age 5, we can summarize age. And what we discover is the first lowest quintile, 196 people, goes 22 to 54. The next quintile is only 8 years. The next quintile, 63 to 68, is only 5 years. And then this quintile is 6 years. And then finally, we've got, you know, what is it, 15 years almost. So these quintiles are useful in all sorts of epidemiology. Here's a function that ranks numeric values only. So, for instance, we've got HDL, high density lipoprotein, for those in the know, and it runs from 14 to 102. But perhaps what we really want to know is who's got the highest or lowest. And so how about if we e-generate, I believe I called it HDL rank is equal to the rank of HDL. And now 66 missing values because I didn't have 66 HDLs were missing. So now when we can summarize HDL and HDL rank, And what we see is the ranks went from 1 to 942 out of the 942. And we can list HDL and HDL rank in 1 through 30, say. And we discover that the first subject had an HDL of 29, which made them tied for 68. The next subject had an HDL of 65, which is, quite a very high one. So they got tied for 885 along with this person. And if you want, we can sort on HDL rank, do that same listing, and find that 14 was the lowest HDL, 17 was the next, 19 was the next. There were 3 tied at 20, they got 5. And then the next several are tied for the 9th position, and so on. And if we list HDL in, let's say, the last, well, let me see, how high did it go? Because I know we have some missings. Well, let's just do that. List HDL and HDL rank if HDL is not missing, and we'll just let it go and go and go and go, and we'll get to the end of the list that way. And what we discovered is that we have some people with an HDL of 92, 941st rank, and one person with an HDL of 102 and scored 942. Now, you might not like these because they're the highest score got the highest. You might want it to go the other way. So you can use track. The shortest number gets the best rank. In field, the highest number gets the best rank. And you can also, there's an option so that it doesn't allow ties. Okay, now this is a function that says for each case, generate the mean across several variables. For instance, we've got 3 values that are scores on something. We'll summarize the scores. There's no missing values, and they're all around 50, and they've got different ranges and different standard deviations. And perhaps we want to generate the mean, so we're going to be using an eGenerate command called row mean. And row mean is the mean of score 1, score 2, score 3. And did I type that right? It looks like I did. And I think I forgot to put the commas in. Oh, that's not what I forgot to do. I forgot to put the new variable name in, which is smean. So after several false starts, we're going to generate a new variable called smean, which is the row mean of the 3 scores. I will now go back to that summarize, and I will add smean. And what you can see is that the mean is basically in the middle of the 3 other means, as is the standard deviation, as is the minimum, as is the maximum. And we can now list and we discover here is the mean of 59, 51, and 62 is 57 1/3. It's true for all of these. The mean works out correctly, and that could be very handy. You can do the same thing to create a median. And so let's do that. I'll go up and reuse this code, excepting I'm going to change it to S median and do it as row median. And here's a trick. You can use wildcards here. And so all the variables that start with score, and we still have to be able to type. And there we go. And now I'm going to list the S median along with the S mean. And the S median of 59, 51, and 62, well, it's the middle of the three, it's 59. And 58, 59, and 39 is 58. And 63, 64, 66, it's 64, and so forth. Here's another useful row function under eGen. You can give it a variable list and have it count how many in that list were missing for that subject. So we've got data in this data set on the various components of cholesterol. Let's summarize those. And here we've got triglycerides, cholesterol, HDL, and LDL. And with 1,008 cases, we've got missings. And clearly, we've got, for instance, more cholesterols than we have LDLs. So we've got patterns of missing. Let's generate a variable called cholesterol missing, C missing, that counts how many of those are missing. And we're going to use an extended generate. C missing is equal to the row missing count of triglycerides, cholesterol, HDL, LDL. And now I have to go back and remember that it's not row missing, it's row miss. Let's list triglycerides, cholesterol, LDL, HDL, and the new variable C missing. And let's see how we did. Well, here's someone who's missing 1, and they get a C missing. Here they have neither triglycerides nor LDL, so they get a 2. This is a complete panel in subject 3, so they get a 0, and so forth. So that can be very handy, especially if you want to do something like describe how complete were your data. Well, 89% of our subjects have complete data. 4% are missing 1. 1% is missing 2. No one is missing 3, but 6% are missing the entire cholesterol panel. Let's talk about converting string variables to numerics. There's a command called encode that takes a string variable name and generates a new variable that is based on the string. And it also creates labels that go along for it. So for instance, we've got a variable called employment. And it's got 4 unique values. They're strings: disabled, full-time, part-time, and retired. Now, if you want to do, say, logistic regression, you probably want these to be numeric codes if you want this to be the predictor value. So let's encode this string as a numeric. And what we're going to do is generate employment cat. So we're going to encode employment and comma generate emp cat. So now if I tab emp cat, well, it looks basically just like employment looks. Disabled, disabled, 275. Full-time, full-time, 155. Nobody who was disabled got coded as any of the others, and so forth. However, if we describe the two employment variables, employment is a string and employment cat is a numeric, and it's got this new label. So what we can do is tab employment cat against employment. We don't need the missings, but if we say don't show the labels, we see that they're actually 4 numbered categories. So we can do say logistic function of whether they are rich or poor as a function of employment, and we can have it treat each of these as separate categories because they're numerics. Now, this was useful because we turned an arbitrary string of however many values with that has alphabetic coding into 1, 2, 3, and 4. And we assigned the numbers to it and then put labels into Stata to remind us which number is which. But if you happen to have numbers like zip codes that was stored as strings, and you want to get the numeric zip code out, you can do that with the real command we talked about earlier. Or there's another command called dstring, which is similar, and you can take advantage of that. Now we have the reverse problem also. Sometimes we've got the number and like employment category, and we want to actually generate the string. Quote disabled, unquote, for instance. We've got a similar situation here with a diabetes treatment category. So let's do a codebook of DMRX, and it's a numeric, and it's either 0, 1, 2, or 3. And zeros are people who are diet controlled, and 1 are on oral treatment, and 2 is on insulin, and 3 is on combined treatment with both insulin and oral. And we might actually want the strings. Now the strings are already in there, so what we can do is decode DMRX. Before we used encode, now we're going the other way, so it's decode. And this time we're going to generate a new variable called, let's call it treatment. And once again, we can tab DMRX and treatment. And interestingly, combined matches combined, diet matches diet, oral matches oral, and insulin matches insulin, but it's no longer the straight line because the new one goes in alphabetical order and the old one did not. But the information is exactly the same. And if we now do it without labels, we discover that the this is the string one and this is the numeric one. That can be very handy. You can also do this with the toString function, which is the opposite of the dstring function I showed you on the previous slide. Now let's talk about labels. We've already talked about them a little bit, but let's get down to brass tacks here. Variables contain values. For instance, the variable sex may contain the values, say, 0 and 1. Variables may have labels. So for instance, the variable KGS, we might forget what KGS stands for. Was that King's General Survey? or was that weight? So we can label the variable KGS with a label to make it more readable. And let's see, we've got KGS, I think. Yeah, but it doesn't have a variable label. So let's label, we only need LAB, the variable, VAR, and we tell it which one we're talking about, KGS, and then we give it a string, and let's call it weight in kilograms. Close the string, and now we get a nice label with it. And so now when we do summarize KGS, or that didn't work, codebook KGS, we get this reminder over here. Now, values may also have labels, and it's the same reasons that we care about variables having labels, to help with readability and to document meanings. So the first thing we have to do is define a label. So we can, the command there is label value, as opposed to label variable, label value, and then you define it. And so we're going to, let's define a label called gender. Label value define gender. Now this has to be spelled out completely. And we've got a gender of 0 is, let's say, female, and 1 is male. Now I didn't put quotes around female and male. I could have. If I needed spaces in those labels or special characters, I would need those quotes, but I don't now. And what did I do wrong? You don't need that label value. It's label define gender. Sorry about that. And now if we can, well, first of all, let's look at gender. Now if we label the values of gender with our newly defined label, gender, and go back up and tab it, now it says female, male, and of course we didn't assign anything to 2, so those 3 cases are just 2. If we say, well, show us that again, but turn off the labels, no labels, we're back to 0, 1, and 2. So Stata is still processing this as 0s, 1s, and 2s. For instance, count if gender is equal to, exactly equal to 1, we get the 458. If we say count if gender is equal to male, it says, what? I don't have anything that's a male. That's because the variable itself is still a numeric. Now, labels are reusable. So let's define a new one. Let's do label define yes, no, where 0 is no and 1 is yes. And we've got a bunch of yes, no variables on here, like senior, which has got this variable label, senior citizen greater or equal to 65, but the values themselves are just 0, 1. So let's label the values of senior, and let's use our new yes, no variable. And now when we tab senior, we know which ones are yeses and which ones are nos. We've also got a variable called warfarin, also 0s and 1s. Let's label the values of warfarin with yes, no, and now it works for that also. We can use the same variable labels over and over and over again, so you don't need to create a new label for every single variable in your data set. Oh, we need to modify our gender label. As you remember, we've got a gender 2, which is not a 0 or a 1. And let's see, we want to call it an other. So what I'm going to do is label, define gender, and I'm going to go to other, and it's going to not like this because, oh, it's already defined. So I'm going to say, well, just modify it. And now, if I tab gender, other has been on there. If you omit the modify option, Stata will generate a fatal error. By the way, in this example, I reassigned 0, 1, and 2, but as you saw me do on the live screen, you don't need to reassign it if you don't want to change it. Now, if this is in a script, and you run the script again in the same session for one that you defined earlier, and then you run the script again, you redefine it, it's going to hit that command and say, well, wait a minute, I can't redefine it gender. So I always stick modify in. So that's a pro tip. Always use the modify option. By the way, labels can have as many categories as you want, so go wild. In fact, I've got code that's got a label for every state in the union, for instance. It's got 50 values plus, Puerto Rico, the District of Columbia, and Guam. So, okay. Let's talk about your assignment. As usual, make a do file, a script, read in module 4 assignment.csv, and label all the variables. Generate BMI, body mass index, to the nearest tenth of a unit, and categorize it 2 different ways. Generate and replace, and then egen and cut. So, and then label those BMI values. Count how many records have no missing values. Create a new variable containing the first letter of the variable study ID. Create a new variable R group that marks a random subset of 25 records, 1 in and 0 not. And create a numeric categorical variable mstat based on marital status. Save the whole thing as module 4 assignment.dta and bring your finished script to class on Monday. See you then. Thank you.